sets, relations and functions. First we will go into the basics of set theory. What do you mean by elements, types, rules, and we shall also go into a new concept for many of you, that is Venn diagrams, which is a part of set theory. So first and foremost we will go into set theory, Venn diagrams and understanding of the rules and the types of sets. Then we shall move on to relations, and thirdly we will cover functions. Already in the previous sessions I have referred to the word functions, but today we shall see what is a function, what type of functions are there, and what are the rules governing functions, range, domain, etc. And then we shall do problems from our exercises, plus we shall cover special problems on the application of Venn diagrams in mathematics. At the end, as usual, I will take up the queries which I received after yesterday's session on AP and GP, arithmetic progression and geometry progression, and I shall be solving some problems where you have found some difficulties. So dear students, let's get going, and we first start with what is object. The first concept in set theory is to understand what is object. I would request you to please open section 7.1. This is chapter 7, 7.1. So we first start with object. Now what is an object? In mathematics, object is something which can be living, non-living, anything in the universe. And when you talk of object, there is a particular term we use, and that is well-defined set of objects. Now if I give a small example, let there be a group. A set is nothing but a group. Okay? When we talk of the word set, it is like a group. Okay, group of objects. Now if I say that there is a set containing objects which are even numbers. So I am saying that there is a set, S-E-T set, or a group containing objects which are even number. Okay? So these are even numbers. Okay? So a set means a collection, a group. We always say this is a set of marker pens. So I am having a green color, I am having blue color, I have a black, I also have another purple, right? So I can say that these four marker pens are part of a set. A set is a collection of objects. Now in this example which I am taking, let us assume that the set which I am about to write is composed of numbers, and the numbers are even numbers. Okay? So that means it will start with 2, 4, 6, 8 and so on till n. Okay? Now, is this a set? Yes, it is a set. Why is this a set? Because it is nothing but a collection of objects. Here, numbers can be an object. Right? Now, the next question. Is this set, is it a well-defined set? Well-defined set. Now, what is a well-defined set? A well-defined set or a well-defined group of objects. So you see, a set is a group of objects. It can be group of numbers, it can be group of people, it can be a group of pens which I am saying, it can be group of any objects. So in this case, I have taken even numbers starting with 2 and it's going on till n, and let us say that n is fairly large. Say n is something like 10,000 till 10,000. Okay? So it's the even numbers starting with 2 and going till 10,000. So it's a collection of numbers. In the last session yesterday we talked about sequence and series. So you can call it a 2, 4, 6, 8. It is a sequence. And since I have grouped them, I have brought them into a group, it is a set. Now, is this a well-defined set? So I think you are clear. It is a set of objects, in this case numbers, and most importantly, it is a set because it contains numbers and it starts with 2 and ends with n, where n is fairly large, n is 10,000. Now, it is a sequence, it is a group of numbers, therefore it is a set. But is it a well-defined set? Well-defined. What does the word well-defined mean? See, the word well-defined means if you can say with certainty, if you are absolutely certain about the numbers which will be there in this set. So if I ask you a small question, in this set, will I be having the numbers 600, 724 and say 5000? Well, these three numbers, 600, 724 and 5000, whether these three numbers will be in this set, right? What do you think? These three numbers, 600, 724 and 5000. These three numbers, will these numbers be included? Will it be included in this set? Will it be included in this group? Answer is yes. Why? Because the set starts with 2. The first element in the set is 2 and it goes till 10,000 and it is composed of the even numbers, and 600 is an even number. So 600 will definitely be included in the set. 724 is also an even number, so it shall also be included in this set, and 5000 being an even number will be included in the set, and all these three numbers, 600, 724 and 5000 are all less than 10,000, which means there is 100% chance, there is 100% probability, or you can call it a certainty, that these three numbers shall be included in this set. And dear friends, this is the reason why these type of sets are known as well-defined set, because you can define each of the element in the set. You are certain that yes, this set starting with 2, 4, 6, 8 going till 10,000 has to contain 600, 724 and 5000. Right? I hope you understand this. So this is the first concept, and that is set and well-defined set. Now what I am doing, friends, is on the right hand side of the whiteboard, I am writing the important concepts which you need to know from this chapter. Since we discussed about what is set and what is well-defined set, I am writing this here. So first is set, and then I am writing well-defined set. The two concepts which we have discussed. If I write all these one by one, it will become easy for us when we recapitulate the points at the end of the session, and anytime when we want to refer to any of these points, we can do it with ease, right? Easily. Fine. So friends, if you now move on to 7.2, so you could see that what is a well-defined set, right? Now let's go to 7.2. Unit point 7.2, the portion 7.2 in your study material. So a set is a collection of well-defined distinct objects. Please see the definition given, page 7.2, and the section is 7.1. We are continuing. Page is 7.2. Please note, page 7.2 and the section is 7.1. So set is nothing but a collection. As I said, it's a group. It's a collection. Like you may remember once again, matrix was an array of numbers. Sequence is a group of numbers. Similarly, set is a group or a collection of well-defined distinct objects. Objects can be anything. Okay? And each object which is there in the set, for example 2, 4, 6, 8, each of the object is known as element. So dear friends, you have to note down number of concepts, number of definitions. You will be learning new terms. So element, and I write the word element here. So we have discussed about what is element. Element means each of the member who are part of this particular set. Each of the members which comprise, which constitute, which build up this particular set. Right? Now we move on to some examples of sets. Further examples. Okay. So object, you know, is every object in the set is an element. Now let me take a particular set A. Now, how do we write sets? How do we write sets? Use the second bracket. You know, this is called first bracket, this is called second bracket, and this is called third bracket. So we normally use the second bracket, sometimes the third bracket also, to write and denote sets. Right? So we are using the second bracket to write another set. Let's set A be the group of vowels. Okay, the group of vowels. Now, group of vowels means A, E, I, O, and U. I close the bracket, I close the set. So, this set A has how many objects? First of all, is it a set? Yes. It is a group of alphabets. It is a group of alphabets. Fine. Second question. Is this well defined? Yes, it is well defined because you know that this set, how am I defining the set? What is the definition of the set? The set is A is a group of alphabets which are called vowels. So it is a set of vowels in the English language. Therefore, all of us know there are 5 vowels. Therefore, A, E, I, O, U. It is well defined because if I ask you whether X is a member of this set, the answer is no, because X is a consonant. It is not a vowel. If I ask you whether I is a member of this set, I has to be a member because I is a vowel. So you see, this is again a well-defined set. I take the other one. Let's take another set, B. Set B is a set which has the permutation of PQR. So I write PQR. It will have the permutation. Now all of you know what is permutation and combination. So if I write the different orders or the different permutations of the letters PQR, what do I get? PQR, PRQ, okay? QRP, QRP, QPR, RPQ, RQP. So how many do I get? 1, 2, 3, 4, 5 and 6. I'm getting 6 elements, 6 members of this particular set B. Is it a well-defined set? Yes. Why? Because it contains, the definition of B is that set B is a set which is composed of the possible permutations of the letters P, Q, R. So this is also well defined. Okay? Now I take the other one, C. I again open by using this second bracket. So, and I write 1, 3, 5, 7 and 9. 1, 3, 5, 7, 9. What type of numbers do you think these are? 1, 3, 5, 7, 9. Well, first of all, they are, you can say, the odd numbers. 1, 3, 5, 7, 9. So it is a set of odd numbers which is less than 10. Okay? So it is a set of odd numbers which is less than 10. So we have 5 members in this set. So this is another type of set. You can see first one we took was the even numbers. Then we took another set comprising of the 5 vowels in the English language. Then we have taken a possible permutation of PQR. These are all groups. These are all collections of different numbers and alphabets. So these are sets. And now we have taken set C, which is comprising of the odd numbers less than 10. Right? That form of writing is not a roster form. It is not a roster form or braces form. It has a different name. It is called set builder form, set builder method. So this is roster form and braces. Okay. Now we move on to what is set builder method is written. Okay. So roster form means where I'm writing the names of all these, directly I'm writing the names of all these, the set of vowels. But here, I have written something different. I am writing x is a variable such that x is equal to 2m, and m is an integer. Integer means a whole number, no fraction. It's an integer. And it is, m is greater than 0 and less than 4. So it means m is greater than 0 but less than 4. And x is 2 into m. Okay? X is 2 into m. Now the question is, m has a value which is greater than 0 and less than 4. And it has to be an integer. So, m can have what type of values? Which values? M can be 1 or 2 or 3. Because as per the given condition, m has to be greater than 0 and less than 4. So, it can assume the values 1 or 2 or 3. And if m is 1, we know x is 2m. So if m is 1, then x will have the values 2. When m is 2, x will have the values 4, the value 4. And when m equal to 3, x will assume the value 6. Because the equation is x equal to 2m. Right? This form is called set for definition. I have defined. I'm not writing the members. I'm not directly writing the members or the objects which are included in the set. I'm writing the definition. I'm building up the set. So it is called set builder. I'm building one after the other. I'm building the set. So it is called set builder method. Set builder form. So if I write this set builder form, if I change it into roster form or braces form, then I'll write that set P comprises of the numbers 2, 4 and 6. This will be 2, 4 and 6 the way I write it, 2, 4 and 6. Okay? This will be the equivalent of this. So this part, if you see, is the set builder method, this entire part, the way I've written it, this is the set builder method, and what you see here is the roster method, roster form or the braces form. So this is the difference between the set builder, or sometimes set builder method is also known as the algebraic method. Algebra, because here we are using algebraic symbols. Equal, greater than equal to, less than equal to, these are algebraic symbols. So it is also called algebraic form, or sometimes it is called rule form, rule. Okay? So the set builder method, I am now writing here set builder method is also called the rule method. Okay, I am creating a rule. Please note, I am creating a condition. I am creating a rule that P is comprising of numbers, that is a variable, such that the variable will be equal to 2m and m is greater than 0 but less than 4. So here I am introducing a condition. I am introducing a rule. Therefore, 2m has to be either, if m is 1, then 2m has to be 2. When m is 2, 2m has to be 4. And when m is 3, 2m has to be 6. And therefore, this concept is known as the set builder method. And this is the roster method or the braces method. I hope, dear students, you are clear now with the difference between the set builder method and the roster method. In set builder, please note, it is also known as the rule method or the algebraic form because we are using algebraic symbols. Now we move on to some more understanding of sets. So we have talked about till now what is a set. We talked about what is a well-defined set. Something where you can say with certainty whether a particular object will be a member of a set. That is called a well-defined set of objects. We saw the roster method of writing a set. We also saw the set builder or the rule method of writing a particular set. So now we can see that when you talk about sets, so it can be anything, like it can be whole numbers, it can be prime numbers, it can be a group of prime numbers, it can be a group of even numbers, right? It can be a group of even the, say for example, say furniture which is there in your house, a set of furniture. So you can write. It can be a set of dressing material, shirts, jeans, hat, a belt, the dresses and the accessories which we wear. It can be a group of that as well. So anything, numbers, alphabets, anything. So now we look at what do you mean by, we also saw what is element. Element means each of the member included in the set is an element. Okay. Now let us look at an important concept. Okay. Now when I am writing a set, say please, you can write with me, please let us write a set. Let's write set, let's give a name to the set. Let it be, say for example, set D. Okay. So I'm writing set D. D is equal to, say I'm writing 1, 2 and 3. Okay. So 1, 2 and 3. So it is a set of the first 3 integers. That is whole numbers 1, 2 and 3. And such that it is greater than 0. Fine. Now, if I write, like you know in case of permutation, if I write like this, 2, 1, 3. That means if I change the order from 1, 2, 3, I am writing 2, 1, 3. Or if I write 1, 3, 2, if I write 3, 2, 1, that means when I change the order, when I change the sequence, okay, will this be another set? That means, please remember the difference between permutation and combination. In permutation, I am sure you remember that the order is important. The order in which the numbers come is important. But in case of combinations, the order is not relevant. The order in which the numbers come is not relevant in case of combination. Similarly, in case of sets, 1, 2 and 3 are the different elements of set D. Fine. Is the order relevant? That means whether 1, 2, 3 and 2, 1, 3, are they same? Are they equal? What do you think? Is order relevant here? The answer is the order is not relevant. So it is like combinations, right? In combinations, the order is not relevant. So here, D is equal to 1, 2, 3 and D will be equal to 2, 1, 3 also. So the order in which the elements come does not make a difference so far as sets are concerned. This is an important part because you might have questions. That's why I discussed this particular part. Okay, now we go to another important concept, something new to learn, and that is set and now subset. Okay, what is a subset? Okay, so let me go to page number 7.2. Please go to page number 7.2 and 7.3. So page 7.2, 7.3 of the study material. Page 7.2 and 7.3. So we will have some more understanding of sets. Now say I am writing like A. A is a set. Let this set be, I'll take 2, 4, 6, 8, 10 and 12. Okay. So 2, 4, 6, 8, 10 and 12. That means it is a set of the first 6 even numbers. Okay. 2, 4, 6, 8, 10 and 12. The first 6 even numbers. Fine. I take another set B and say this is 4, 6 and 10. I take another set C and this is 2, 4 and 12. Okay. Please see the sets once again. Set A is 2, 4, 6, 8, 10 and 12. That means it is a group of 6 numbers. And can you define the numbers? Yes, the numbers constitute or the numbers comprise the first 6 even numbers. Right? 2, 4, 6, 8, 10 and 12. Fine. Set B is having the numbers 4, 6 and 10 and set C is having the numbers 2, 4 and 12. Do you see any relation between A and B? First, let us concentrate between A and B. So please see that every number which is there in set B, 4 is also there in set A. 6 is also there in set A. 10 is also there in set A. So we say that set B is a subset of set A. Right? Please note this. Set B is a subset of set A. And we write it like this. So I will write B is a subset of A. So we use this symbol. Okay? It is a subset of A. Okay? So I will write B is a subset of A. This is how we write. So in this case, B is a subset of A. So it is like, like father and son or father and daughter or mother and daughter, mother and son. This is a bigger one and B, every element in B is there in set A. Every element of set B is there in set A. So you can call it like a parent and son or parent and daughter relation. So you can see that all the elements here are contained in set A. So B is a subset of set A and set A is a superset. We use a new term, superset. So B is a subset of A and A is a superset of B. So please note these terms. So I'm writing subset here, subset and superset. Okay, so we have to undergo, we will be going through different, in this chapter, different terms, new concepts. So we have to keep on writing. And I request you, just as I'm using this part of the whiteboard, to write down the names of the new terms. Similarly, in your exercise book, in your scrapbook, please go on writing these new terms and later, after the session is over, you can compare it with the study material and you can have a complete picture, right? You can refer the study material according to the discussion we are having. Fine? So, dear students, you can see that there are two relations here. B is a subset of A. B is a subset of A because all elements in set B are there in set A. Also, set A will be a superset of set B. Okay? Like we say B is a daughter of A. So A is the father of B. Like this relation, inverse relation. Right? Now let us look at C and A. Please see the set C. We have the members, the objects in set C. We are having 2, 4 and 12. These are the elements, right? The elements in set C, 2, 4 and 12. The elements in set A, 2, first of all. Do we have 2? Let's check. Yes, we have 2. Fine. 4, do we have 4? Yes. 12, do we have? Yes. So again we say that set C is a subset of A, and again A will be the superset of C. So dear students, this is the basic concept of set. We talked about element, how to write a set. There are two formats. First is the roster form, okay, or sometimes you call it the basis form, and the other is the set builder method, where you define the relation. You can use an algebraic form or you can use a rule. After that, we talked about the relation between a bigger set and a smaller set, and the relation is such that all elements in the smaller set are there in element, the bigger one. In other words, all elements in set B are there in set A. So set B is known as the subset of A, and we write it like this. You can see here B is a subset of A. Same for set C, because all the elements in set C are there in set A. I think you are clear till here. No problem in understanding. Simple concept. This chapter is simple, but there are some new concepts and some new terms. Okay, we need to understand each of the terms clearly, and the problems will be easy. If you talk about the weightage of this chapter I discussed yesterday, definitely 2 to 3 problems are expected from this chapter, because it has 3 distinct divisions. First is the set theory. We are doing set. Then we will do Venn diagrams. Then we have relations, and then we have functions. So the entire chapter has 3 distinct parts: sets and Venn diagram, relations and functions. Okay, so therefore we expect 2 and 3, sometimes 3 problems come, and therefore you should be definitely clear with this chapter, and we are going through each of the concepts in line with the discussion given in the study material of the institute. Okay, so we have seen what is subset and what is superset. Okay, now we go to some more concepts. Okay, some more terms will be now discussed. I will be discussing some more terms. Fine. So we have seen what is an element, we have seen what is a subset, what is a superset, and now let us talk about another term which is called a proper subset. Proper subset. What is a proper subset? Now say, for example, I have 2 sets here. Say A equal to A, E, I, O, U. And we have set B, which is A, E, O. Okay? Okay. Please see the sets. Set A comprises of the elements A, E, I, O, U. Set B comprises of the elements A, E and O. Now, we can call it, the relation is such, you can see every element in set B, A, is there in set A. E, the second element, is there. O is there. Okay? So if you do one-to-one mapping, okay? Mapping, you can see A, E, E, O. That means definitely we can write B is a subset of A and A is a superset of B. I'm sure you can see the relationship. Now please note, since B, but can you say, the question, B is set B, can I say that B is equal to A? Can I say this? No, I cannot say. I cannot write whether B is equal to A, B is not equal to A. Why? Because every element in the B, in the set B, and every element in set A are not the same. Set A is bigger. Set A has two additional letters which are not there in set B. So in fact here A is greater than B. Now in this type of condition where B is a subset of A, B is a subset of A, but B is not equal to A. In this condition we write that B is a proper subset of A. So please note the new term proper subset. I am writing here proper subset. It's a proper subset. That means a set will be a proper subset. Say for example two sets X and Y. If X is a subset of Y, but X is not equal to Y, then we will call it X is a proper subset of Y. Okay? I hope you understand this. The concept of subset, superset and proper subset. Okay. Next concept. One by one we are covering very easy concepts, and these are standalone concepts because you just jot down these concepts together and they are not connected as such. Each is independent. Okay. Now we move on to a new term, which is, I used the term, I asked a question whether B is equal to A. So we will now see what do you mean by equal sets. Equal sets. Okay. So if I write A is say 2, 4 and 6. Okay. A is 2, 4 and 6. And if I write B is equal to 6, 2 and 4. Please see the sets. A is 2, 4 and 6. A is 2, 4 and 6. B is 6, 2 and 4. Are they equal? Just see. Now, every element in B, do you find the same elements in A? A is 2, 4 and 6. B is 6, 2 and 4. So you can conclude that every element of set B is included in set A. So A is equal to B. A is equal to B. So these two sets are equal sets. These are called equal sets. So I write equal sets here. The next concept we have done, equal sets. So this is the concept of equal sets, where they have the same number of elements. Here also we have 2, 4 and 6. So 3 elements. Here we have 6, 2 and 4. 3 elements, and each of the element is same. So they are equal to each other. These are called equal sets. Right. Now we see what is equivalent sets. Not equal, but equivalent. Okay. So now instead of equal sets, I'll write equivalent. Equivalent sets. Okay. Now I'm writing two sets. Okay. Say I have A. A is say, okay, 1, 3 and 7. 1, 3 and 7. Set B. 2, 4 and 6. So I have A. Set A is 1, 3 and 7. And set B is 2, 4 and 6. Okay, 1, 3 and 7. Set B is 2, 4 and 6. Are they equal? No. Now please note that they have the same number of elements. Set A has 3, so I'll be writing set A has 3 elements. Set B also has 3 elements. In other words, the number of elements NA is equal to NB, and this is equal to 3. Please see, the number of elements in set A and the number of elements in set B are the same. They have 3 elements each. So this type of set, in this case, set A and B are said to be equivalent sets, but they are not equal. So there's a difference between what is equivalent set and what is equal set. In case of equal set, definitely the elements in one set and the elements in the other set will be same, will be identical. Plus, the number of elements in one particular set will be equal to the number of elements in the other set. In that case, we call them equal sets. But if we find two sets where the number of elements are same, but the elements themselves are different, in that case, they are not equal sets. They are known as equivalent sets. Okay? So you can understand that I can write that, please note this line, that equal sets, two equal sets have to be equivalent, but two equivalent sets may not be equal always. Okay, once again, two equal sets have to be equivalent also, but two equivalent sets may not be equal always. I hope you do understand this. I'm sure you are clear till what we have discussed. So, equal sets, now we write one more term which we discussed, that is equivalent sets. Okay? So, number of ideas and number of concepts we have to see. So, I have given the example of equivalent sets, but they are not equal. Okay. Now we go to the next definition or the next concept, which is called universal set. Universe. Okay, universal set. So what is universal set? Universal set. Now, say I write a set such that the set will comprise of integers which is less than 10. So, if I use the roster form or the braces form to write the set, what is the logic? What is the rule given? What is the condition given? The condition is that it is a set of numbers, and the numbers are integers. That means they are whole numbers. They are not fractions. They are complete numbers, and the numbers are less than 10. I mean, the numbers all will be less than 10. So I can write the set, it will be 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So I am having these numbers, and this set, in this example, in this particular example, will be called the universal set, shown by the letter U or by the letter S. So please note that universal set is shown as U or S. Now I am writing two more sets, P. I am writing a set P. Set P is, say, let me write set P. Okay, set P is, let it be 0, 1, 2, 4. And set Q is, say, 5, 6, 8 and 9. So we are having two sets, P 0, 1, 2, 4, and we have Q 5, 6, 8, 9. Okay? Now, S is the universal set. S is here the universal set. S is either shown by the letter U, it is denoted by the letter U, or sometimes you will be seeing that it is denoted by the letter S. U or S. Clear? Fine. So the numbers you can see here is from 0 till 9. They are integers and they are less than 10. You have set P here 0, 1, 2, 4 and set Q 5, 6, 8, 9. So the first relation which I get is I write that P is a subset of S. I'm sure you agree to it and there is no confusion in your mind regarding this. Second relation, the numbers which are there in P, the members, the elements of P, right, are there in S. Fine. But is P equal to S? No. So I can write that P is a proper subset. It is a proper subset of S. This also I can write. Fine. Secondly, Q. Let us look at Q now. So P is done. Now let us look at set Q. Please look at Q. Q we are having 5, 6, 8, 9. 5, 6, 8, 9. Okay. Now you can see even Q is a proper subset of S. So we have understood what is universal set. Universal set is a set which comprises of all the elements under discussion, right? And we saw in this example that both P and Q are proper subsets of the set S. S is the universal set in this particular case. Now, here we will also see another concept, and that is called complementary set. Now, complementary set means what? P, let us look at P. P has 0, 1, 2 and 4. But if I ask you that what are the elements which are there in S but which are not there in P? Once again, what are the elements which are there in S, in the universal set S, but the elements are not there in P? That means elements belonging to S which are not included in P. So let us write the numbers which are there in S but not there in P. So I am creating a new set here and I am writing, so 0, 1, 2, 4, okay. So 0, 1, 2, 4. So 3 is not there. So I write 3. 5 is not there. 6, 7, 8 and 9. So it's a new set. This set is called the complementary set of P and it is shown by P dash. P and then a small dash at the top. This is called the complementary set of P. That means P dash here will be those numbers 0, 1, 2, 4. 0, 1, 2, 4 is there. But 3, 5, 6, 7, 8, 9 is not there in P. But it is there in S. S is the universal set. Right? Therefore, P dash means complement of P. The complementary set of P. Right? And this is shown by P dash. Now I would request you, can you quickly find out Q? The set Q is given 5, 6, 8 and 9. Can you find out Q dash? That means what are the elements which are there in S but which are not there in the set Q? Let us identify 5, 6, 8, 9. So 5, 6, 8 and 9. So in Q dash, the complementary set of Q, 0 is not there. So I write 0. So Q does not have 0. 0, 1, 2, 3, 4 and 7. So please note Q dash. Q dash is 0, 1, 2, 3, 4 and 7 because the set Q does not possess the elements 0, 1, 2, 3, 4 and 7. But these elements are there in the universal set S. Okay? So please see the concept of universal set denoted by either S or denoted by U. Then I talked about proper subset. You can see in this case, both P and Q can be defined as a proper subset of S because they are a subset of S and they are not equal to S. Plus, we have found out the complementary set. So, after equivalent, I write complementary. We have discussed about complementary set. And we have also discussed about universal set. Universal set. So, till now, if you quickly recap, right, almost it's going to be 1 hour. We have started with the definition of set, right? We discussed about what is a well-defined set. Then we talked about elements. We moved on to roster form. Then we discussed about the set builder form or the rule method. Then we talked about what is subset and what is a superset. Thereafter, we proceeded to discuss about proper subset, which I discussed here also. And then we went into equal sets. I discussed about the difference between equal set and equivalent set. And now we talked about complementary set and universal set. Okay. Now some numbers again. So just wrap this up. And now we go on to the next point. In case of a set, how many proper subsets will you have? So let's look at this. Okay. Now, say we have a set containing n elements. Okay. A set which has n elements. Number of elements is n. By definition, how many subsets will it have? The number of subset it will have is 2 to the power n. So number of subset will be 2 to the power n. Therefore, if a set has 3, if n equal to 3, that means if a set has 3 elements, then the number of subset, SS, subset will be 2 to the power 3, that is 8. Please note this formula, this is important. So, number of subset. So, I write here, the next thing is number of subset, that is 2 to the power n. 2 to the power n. Right? Now, if I ask you out of these subsets, how many are proper subset? Okay? It is easy. It will be 2 to the power 8 minus 1, that is 7. Because out of the subsets, now if I ask you to write, let's write the subsets. Okay, let's write the subsets and see what happens. Say we have 1, 2 and 3. So, how many subsets will be there? Okay, so we can have 1, 2, 1, 3, 2, 3 and separately we can have 1, 2 and 3. So altogether we can have 6, but we also have one more and that is 1, 2, 3 itself will be a subset. And in that case it will be an equal set of course, right? Plus we have another set which is called the empty set, which is shown by this, also shown by this, null. It is called a null set. This is called empty, null set or empty set. Okay, is shown by this. Or by an empty, you go, nothing is inside. Okay, nothing is inside. So just two brackets, but nothing is inside. This is called an empty set. Right. So this will be 1, 2, 3. If you talk about 3 elements, what will be the sets? We will have, let us write the sets. We can have 1, 2. We can have 1 and 3. We can have 2 and 3. We can have 1 only. We can have 2 only. We can have 3 only and we will have null set. So these are the proper subset. So how many are there? 1, 2, 3, 4, 5, 6, 7. 7 proper subset, and that is what we have found out, 7 proper subset. The 8th set, the last one will be the set itself. That is 1, 2, 3 itself will be another set, a subset. But but in that case it's an equal set. Okay. So this was another important concept, null set and empty set. So I write null set here. You understand now, I'm sure, what is null set or empty set. So this chapter, once again, dear friends, be very attentive in the session as I go on explaining each and every concept, because here you will have to learn many new terms. See, permutation, combination, number of terms was very limited, but here you see so many terms already, almost 10 to 12 terms we have learned. Okay, so therefore please, listen carefully and note down the points which I am writing here, so that for every concept I am giving an example. Please note the example, so later on when you revise on your own, you won't have any difficulty in understanding. This chapter has many new concepts, okay, many new definitions, many new terms are there. Okay, so now we proceed, and now we are going into, so complement we have done, complementary set we have done, we have also done what is universal set, what is empty set or null set I have discussed. So many of the important concepts already is over. Okay, now we will go into cardinal number, and then we will go into set algebra. Okay, two more concepts are there. Cardinal number. So cardinal number is basically, if I write A, set A, say set A I am writing, say it is, once again I am writing, say A, E, I, O and U. How many elements are there? 5 elements. 5 numbers, 5 alphabets, 5 letters, A, E, I, O, U. So here I will say that the set A has a cardinal number which is equal to 5. So what is cardinal number? The number of elements of set A, N, NA. So NA is equal to 5. Okay. So please note that here set A has 5 letters, A, E, I, O, U. So in other words, it has a cardinal number of 5. Right? So please note this. So again I write here the new concept, cardinal number. Okay? Cardinal number. Now we go on to power set. What is power set? So let's look at, this is the last definition we will learn for the time being, and then we will go into Venn diagrams and set algebra. Okay. So let us look at what is power set. Power set. So we see what is power set. Okay. Now power set means the collection of all possible subsets. Okay. As I said that if A is equal to say 1, 2 and 3. So what will be the power set? First of all, power set, PA, power, powerful, all powerful, right? So we say all powerful means full power. So if you give full power to the set, what will be the elements of the power set? It will have, let me write the elements. I write the third bracket first and then I include them in second brackets. First will be 1 and 2. So we are having 1, 2, I'll take 3 also, 1, 2, 3. So first will be 1 and 2, then we have 1 and 3, then we have 2 and 3, then we have only 1, then we have only 2, then the other set is only 3, then we will have another set 1, 2, 3, and then I'll have the empty set or the null set. Let me see if I have written it correctly or not. Let me review, and I request you to review with me as well. So power set means the set of all possible subset. So set A is 1, 2 and 3. So what can be the possible subset? 1, 2 is a subset. That means you know the subset symbol is this. So 1, 2 is a subset. 1, 3 is a subset. 2, 3 is a subset of A. Only 1 is a subset. Only 2 will be a subset. Only 3 is a subset. 1, 2, 3 itself will be a subset of 1, 2, 3, but this will be an equal set also, right? It is an equal set. And finally the empty set, also known as the null set. null set, right? Null set. This is how we write. So this is also an element. So let us count how many elements are there in this particular power set. Okay? So I have 1, 2, 3, 4, 5, 6, 7 and 8. 8. And that is what we wanted to prove. Right? Because a power set means all possible subsets of a given set. So once again, please review. Set A is having 1, 2 and 3. Okay? The 3 elements are 1, 2 and 3. Please note. And we have the subsets, the possible subsets are 1, 2, 1, 3, 2, 3, 1, only 2, only 3, 1, 2, 3, and the last one is the empty set or the null set. So in all we are having 8 subsets of set A, and power set is the set of all possible subsets. So that is what we have done, dear students. What we have done is, you see I have taken the third bracket here, third bracket, to show that power set is a set of all possible subsets. It is a set of all possible subsets inside. Okay? So this is called a power set. Fine. Now we move on to set notations. So many of the concepts we have done. Let us quickly review what are these concepts we have done already. And I request you to also see whether you have noted down these definitions and these terms. Started with what is a set. I discussed about well-defined set, definition of a well-defined set. Then I moved on to what is roster form, braces form, and then the set builder method or the rule method. Then I talked about what is subset and what is a superset, the relation between two sets, subset and superset. Then I talked about and explained what is proper subset. After that, we went into equal sets, the concept of equal sets and the difference between equal sets and equivalent sets, right? Equal sets and equivalent sets. Then we discussed about complementary sets. And thereafter we went into universal set, discussion of universal set. Number of subset we saw was 2 to the power n. And then I referred and explained about what is a null set or an empty set. We also saw the cardinal number of a set, which means the number of elements in a set is called the cardinal number. And finally, we talked about power set. With this, we come to the end of the first part and we move on into the second part, and that is set operations. Okay. Now we go to set operations. So we are like doctors now operating. Okay. Now, one operation already you know, and that is complementary set. The other two operations are, one is called the union of two sets, joining of two sets or addition of two sets. That means you are actually adding two sets. It is shown by the symbol U. Okay? Set notation. So once again, let me see the set notations. Okay, so set notations. Let me write first. Set notations. I will request you to copy this in your notebook, and these are some new symbols you are learning, so please keep a note of it. The first one, number 1, okay, number 1 is called union of two sets, union of two sets. It is shown by the symbol U. The next one is known as the intersection, the intersection of two sets, and it is shown by the opposite sign. So this is becoming this. Number 3, null set. Null set I already shown. It is shown by this. Okay. The fourth one, you know, subset. How do you show subset? B is a subset of A. So I write B is a subset of A. Please see the notations carefully. And if I say that there is a set, A is equal to say 1, 2, 3, then I will write 1 is an element of A. So once again, union means the addition of two sets. It is shown by a U. Intersection, we will see what is intersection. Intersection of two sets means the common elements of two sets. It is shown by this symbol, inverted U. Null set is shown by this symbol. Subset is shown by U but in a horizontal way, and element is shown by this symbol. So we have to remember 5 distinct symbols, because now we shall be using set notation. These are called notations. This is a notation. Okay, these are notations. Symbols. Okay. I hope it's clear. Right? So, we have 5 notations for set, and now we shall enter into the next part where we talk about the union, intersection, etc. So please take a snapshot of this. Please note this so that you don't forget. We will now proceed to have a look at the set operations. Okay. Set operations. Okay. So we will go into set operations, and first we look at union. Okay, so I will write some numbers once again, and now also we shall see Venn diagram. Okay, Venn diagram. So if I write the set A equal to 2, 3, 6, 10 and 15, 2, 3, 6, 10, 15, I close the set. Okay, so set A is 2, 3, 6, 10 and 15. Please note it. 2, 3, 6, 10 and 15. Now I will write the other set, that is set B. B is 3, 6, 15. 3, 6, 15, 18, 21 and 24. Okay, please check the sets once again. Set A is 2, 3, 6, 10 and 15. Set B is 3, 6, 15, 18, 21, 24. I want to find out A union B. A union B. So A union B. That means A plus B. A plus B or A union B means we have to create a set of elements which are there in either A or B or both. Okay, you see there are some elements here, like take the case of say 15. 15 is there here also. 6 and 3, it's there in A, it's there in B. Okay, but there are some elements in B which are not there in A. Take the case of 18, 21, 24. These are there in B. Okay, but these elements are not there in set A. Please see. So A union B means the summation of two sets such that the elements which are there in either A or B or in both will be included. So let us write A union B. 2 included, because 2 is there in A but not in B. 3 and 6 both in A and B included. 3 and 6. 10 is there in A but not in B. It is included. 15 in both included. 18, 21, 24. It is there in B but not there in A. So included. 18, 21, 24. So this gives you A union B. Please have a look at A union B. Please be very careful in understanding. right? And make sure you are clear with each and every concept. So in this list, I am now going to add union because we have discussed about union. Union U. So this is how we add two sets. In other words, union means addition, integration, amalgamation, whatever name you give it, grouping together, right? And what I do is, say for example, I take a very easy example. Say you have 3 books on mathematics. I have 1 book on mathematics, the same one of the common books, and I have 2 books on law, which you don't have. So you have 3 books on mathematics. I have 1 book on mathematics, which you also have, but I have additionally 2 books on law. You have 3 books, I have 3 books. You have 3 mathematics books, I have 1 common mathematics book and 2 books on law. You have a set of 3 books, I have a set of 3 books. You add them. What will you include in the set? 3 books which you have definitely will go. This will also include 1 book which I have, you also have on mathematics. And the 2 books on law which I have but you don't have, that also gets included. So in the addition, if you do a union of these 2 sets, you will have 3 mathematics books and 2 law books. So this is the concept of union of 2 sets. Addition of 2 sets, grouping together of 2 sets, integration of 2 sets. I hope it's clear. This is A union. Now we go to what is A intersection. Okay? And then we will show it through Venn diagram. What is intersection? Now, intersection indicates the common elements. So intersection, A intersection B means the common elements which are there in both A and B. So I am writing here the common elements which are there in both set A and which are there in set B also. Let us create set A intersection B, and let us see which are the common elements which are there in both set A and set B. I will mark it with a green color. Okay, so 3 is there, 3 is there. 3 I write. 6 is there, 6 is there. 6. Okay, then you have 15. Yes, 15. Okay, so I write 15. Anything else? No. 3, 6 and 15, 3, 6 and 15. So I close this set. A intersection B is 3, 6 and 15. Please see, this is the concept of intersection of 2 sets. So we have seen union and we have now seen what is intersection also. Intersection. Right? Now we show what is a Venn diagram and how we can use Venn diagram. You will understand how it is depicted through Venn diagram. Now Venn diagram, dear friends, is also called Euler Venn diagram. Euler was a very well-known mathematician. So Euler Venn diagram. Now when we are using a Venn diagram is shown like this. So I draw a sample space here. 2 sets A and B. This is A, this is B. Set A, set B. This is called a Venn diagram. V-E-N-N. Venn diagram. Clear? Right? Venn diagram. Now we have 2 sets A and B. A union B means, I will color it. Okay? First I will color A union B. A union B means everything which you see here. A union B. Okay. This is A union B. right? That means A union B means the entire region here. A union B. The region outside A and B, this is the universal set. This full rectangle which you see is the universal set S. Or you can call it U, whatever, S or U. This is the universal set. You have set A here and set B. So the shaded region which you see now is A union B. This is A union B. A union B. Now we shall draw A intersection B. Okay? I'll just make this a little smaller. Get some and draw another one. This is a universal set. Now we draw set A intersection B. Okay. Another diagram. This is the universal set U. I draw one set here. I draw another set here. So this is A and this is B. I am trying to draw A intersection B. A intersection B means set A and set B, the common areas. Okay? Please see that the two sets are interconnected. They are coming closer and they are overlapping. They are overlapping. They are not separate. They are overlapped. The overlapping portion, let us identify the overlapping portion. Please see the overlapping portion is here. This part. I am shading it. Right? So this part which you see, which I am shading, is A intersection B, A intersection B. The common area of both set A and B, whereas this shaded region is A union B. So two of the most important set operations we have completed. Union and intersection. If I ask you in this particular area, what is the universal set? The full thing is the universal set. Set A is here, set B is here, this is A intersection B, and this is A union B. Addition of two sets. Right? This is called Venn diagram. So union we have done, intersection we have done. I am taking another example. And we shall find some intersections. So A, say A is equal to 2, 3, 6, 10 and 15. 2, 3, 6, 10 and 15. And C, set C is 2, 5 and 7. Fine. So A is 2, 3, 6, 10 and 15. C is 2, 5 and 7. 2, 5 and 7. If I ask you that A intersection C is what? A intersection C is only one element is there which is common, that is 2. So the answer is 2. A intersection C will be 2. So please remember, this is the photo, this is the picture for, the diagram for in union of two sets, the addition of two sets. So in this shaded part you can see this part is only A, this part is only B, and this common part is both A and B. In this particular diagram you can see the shaded part is the common area of both A and B, so that is called intersection. Right. I'll take some more examples. I probably write it here. You have seen this. I'll just rub this and write some more examples, and let's see if we can find out the intersection. So this is say set A is set A is 1, 2, 3 and 4. So 1, 2, 3 and 4 set A, and we have set B. Okay, we have set B equal to 3, 4, 5, 6. 3, 4, 5, 6. So A intersection B is, first of all, A union B. What will be A union B? All the elements which are there in A and B. So 1, 2, 3, 4, 5 and 6. This is A union B. A intersection B. What will be A intersection B? Those elements which are common to both A and B. Those elements which are there in both A and B. So in A and B, what are the common elements? You have 3 and 4. So the set 3 and 4 will be A intersection B. And A union B is already there in front of you. Do have a look once again. A union B, A intersection B. I think it makes sense. And you are able to follow and understand. Okay. So union intersection is done. And Venn diagram, I think you have understood. This is called Venn diagram. Please see 7.2. This is there in 7.2, part 7.2 of our study material. So you will see that set operations can be shown through Venn diagram also. This is the union, this is the intersection. Okay. Now we go to two very important formula, which we have to remember. You can call it theorems, you can call it formula. So theorem 1 and 2. So I will write theorem 1 and 2. Okay. This is an important theorem and I keep the diagrams as it is because we will need to refer to the diagrams. I am first writing theorem 1. Theorem 1. Theorem 1, that is rule 1, you can call it rule 1. Rule 1 says that A union B is equal to A plus B minus A intersection B. That means the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. Okay? So, please see the Venn diagram once again. A union B. A union B means A. Let me once again, I take A first. So full A I am shading, full A. Please see I am shading the common part also, full A. I have shaded full A. Full A. Plus B. So again I am shading B. B I am shading. And in the process I am also shading the common part once again. So A is shaded, B is shaded. But I have shaded the common part 2 times. Please see. I shaded once full A. Common part is shaded. Again I am shading part common set B. Set B and the common area is also shaded. So I deduct A intersection B once again. I have to deduct once A intersection B so that I can get A union B. Because I have shaded the common part 2 times. So I have to adjust. So I deduct once. It is like plus 2 minus 1. So you get plus 1. Right? So this is A union B and how we show it. Now this is for 2 sets. If you have 2 sets, A and B. But if you have 3 sets, P, Q, R, 3 sets. What is the formula? So P union Q union R. For 3 sets, the formula is a little bit longer, but I'm sure you will be able to remember it. It is NP plus NQ plus NR minus N of P intersection Q minus N of P Q intersection R minus N of P intersection R plus N of P intersection Q intersection R. So this is the formula for 3 sets. You have P, Q and R, right? You have 3 sets here, P, Q and R, and we are having 3 sets, a little longer formula. So first is NP, only P, plus NQ, only Q, plus NR, only R, minus P intersection Q, that means the common part of PQ is deducted. Then Q and R, common portion is deducted, minus P and R, common part of P and R is deducted. And now we add back P, Q, R's common part together. I will use this one to show you. This diagram, I will now make it into 3 sets. Right? So we will have 3 sets. P, Q and R. Okay? So this is P, this is Q and this is R. So the idea is, here you see P and Q. The common part is this. I have used angular green with green. Now I am using blue to show the common part between P and R. Okay, I am using blue. This is the common part of P and R. And the common part of Q and R. Okay, I am using purple. So this is the purple color. I am using like this. Now if you look at the common area of P, Q and R, the common part of the 3 circles, this is the common part. This part, which I am darkening now, I am darkening it. Okay, this part falls in P also, this part falls in Q also, this part falls in R also. This is the common part. This is this expression. P intersection Q intersection R. This part. So this is what happens in case of 3 sets P, Q and R. Okay. Now we go to page 7.8. So this is all we need to know for the time being on Venn diagrams. I have discussed about Venn diagrams, also called Venn Euler diagram, and we are strictly following the study material and making sure that all the points are covered one by one. So this is the Venn diagram, and we talked about the union of 2 sets, the intersection of 2 sets, and I also discussed about theorem 1 and 2. First theorem is A union B, and the second theorem is for 3 sets. What is the rule for 3 sets? Okay. So now let us move on to the next concept, which is unit 7.3, page 7.8 of the study material, page number 7.8 of the study material, and this is product set. We go into product set. Okay. So I will have to rub this part. I hope now you are clear with Venn diagrams, A and B, union I showed you, here I showed you the intersection, and here I showed you the 3 sets P, Q and R. What are the common areas? PQ, QR, PR, and then PQR, the common shaded area, this one. Okay, so I'm rubbing this part, and now we will move into the product set. Next concept is product. 7.3. So we move on to unit 7.3. Kindly move to page 7.8 of the study material, and please see the heading is given product set. So this is 7.3. So product set. Now product set, or sometimes called a Cartesian product. You see, Cartesian product. So very similar to matrix multiplication. So if say set A is given, so we are doing product set now. Product set. So A is given 1, 2 and 3. 1, 2 and 3. B is given 4 and 5. So the product A into B, it is a set. So I first open third bracket. Okay. A is given 1 into 3. B is 4 and 5. We have to find out the product of these 2 sets, or Cartesian product. Okay. It is called Cartesian product. Okay. Cartesian product. Sets. So the multiplication will be like this. Let me show you the order first. 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, 3, 5. So first is 1, 4. So set 1, 4. First. 1:1 mapping. 1:1 mapping. First here, then here, then here. Okay, one first direction, second direction, third direction. 1, 2, 3. 1 is 1 to 4, done. Now 1 to 5, 1 and 5. Then 2 and 4, so I write 2 and 4. Then it is 2 and 5, so I write 2 and 5. Then 3 and 4, so 3 and 4, and I write 3 and 5. And I close the third bracket. This is as simple as this. This is called product set or the Cartesian product of two sets A and B. Okay, so 1, 2, 3 and 4, 5. Set A is 1, 2, 3. Set B is 4, 5. So the product is given by the set A into B. So we have set, the elements are set 1, 4, set 1, 5, set 2, 4, set 2, 5, set 3, 4, set 3, 5. Okay, so this is how we do product set. Now we go to page 7.9 and we start with relations and functions. Okay, so we have done theorem 1 and 2, we have done product set, we have also done Venn diagram. So many things one by one we have done. Okay, we now move on to relations and functions. Second part, this will not take so much of time. In fact, the first part is the biggest part, the longest part. This chapter is fairly long, not an easy one, and new concepts are there and we need to understand each and every concept because question can come from anywhere. So I think a full 2 hours, probably we will take few minutes more to complete this chapter. It cannot be done in less than 2 hours. If I do it, it will be a wishy-washy way, which I will never do. So we'll take time and devote entire 2 hours, and maybe like other days, we'll devote more time to complete, right? So now we will go into relations and functions. Each concept is important. None of the concept is very difficult, but you need to know each and every concept clearly. Okay. We are proceeding now to unit 7.4 and the page number is 7.9. Okay. Now we see what is called image. Okay, image. Right. And we have the basic concept of relation. Okay. So now I am drawing or writing a simple, set and trying to build up a relation between two sets. Say A is equal to 2, 3, 4. 2, 3, 4. And B, I will be writing set B, but the relation, now I come to the word relation because now we have started with relations and functions. Relations and functions, you can see, relations and functions. So now we will talk about the relation between two sets. We know everything about set. We have done what is set, right? Discussed about roster form, basis form, set builder method, subset, superset, proper subset, equal set, equivalent set, what is a complementary set, the concept of universal set, number of subset, that is 2 to the power n. Then we talked about cardinal number, what is a power set, set notations, U for addition, reverse U for intersection, and this for inverted U or horizontal, if you put U, that is for subset notation. Then we did the union of two sets NA plus NB. We did the intersection, theorem 1 and 2, and product set. So, plus we did the Venn diagrams. With this knowledge, now we are ready to move into relation of two sets. Now, the relation is like this, that A and B are two sets which are non-empty. Non-empty means at least one number is there, one element is there. If you have a set like this, say 5, it is a non-empty set because you have at least one element and that is 5. So it is a non-empty set. Non-empty set. So A and B is linked, relation, okay. We are building a relation between A and B. A and B, we write it like this, A arrow B, such that the set of B, okay, the set B and the set A will have a relation, and the relation is the elements in B will be 2 into X, where X is the element here. Okay, so for every element in A, B will be 2 times, 2x. X is, if you consider X 2, then B, the first element will be 4. If you consider 3, the second element will be 6. And if you consider 4, the third element will be 8. So now, I have got a relation between the two sets A and B. Okay? A and B, 2 sets. The relation is 2x. Fine? And you can see for every element, there is a corresponding element here. 2 and 4, 3 and 6, 4 and 8. So please note that we are having now 6 numbers. Again, a matrix is drawn. Set A and set B. We have 2 here, we have 3 here, we have 4 here. Right? Number of concepts we'll learn from here. Please pay attention and please note down these important points. So 2, 3, 4. And the result is 4, 6 and 8. This is mapping. It is called mapping. Mapping. There's a relation. Relation is B is 2x. Right? Where x is an element of A. Please note that this 2, 3, 4, very important concept. 2, 3, 4. 2 is linked with 4. 3 is linked with 6. 4 is linked with 8. So 4, 6 and 8 are called the image of 2, 3 and 4. 4 is the image of 2. 6 is the image of 3. 8 is the image of 4. So this column is called, B is called the image. B is called the image column. Image. Image means reflection. Reflection. Image. Okay? So 2 is linked with 4. So 2's image is 4. 3 is linked with 6 because 3 into 2 is 6. 3's image is 6. And 4's image is 8. So the column B which you see here is called the image column, and like we saw the relation between subset, and we talked about subset, you remember, and superset. Same thing here, subset, superset. So the relation is 4 is the image of 2. So 2 is the pre-image, pre-image. So A, column A is the pre-image. This column is the pre-image column. Okay, pre-image. And image is B. So 4 is the image of 2. 6 is the image of 3. 8 is the image of 4. And 2 is the pre-image of 4. 3 is the pre-image of 6. And this 4 is the pre-image of 8. So I will also write here, please note image and pre-image. We have discussed image and pre-image. Please note in your scrapbook one by one the relations. Now we have moved into relations. So image and pre-image and mapping. This is the concept of mapping and pre-image. Okay, now we will learn about the next concept. What is range and domain? See, I have taken a very simple formula that function of x, here it's 2x. The relation between A and B is that every element of B is 2 times the element of A. The relation is 2x. Similarly, there can be a relation, can be say logarithm of A. So if you have 1, 2, 3, 4, B will be log 2, log 3, log 4. You can have a trigonometric relation, of course it's outside the curriculum. You can have something like 1 by x. So if it is 2, 3 and 4, B will be 1 by 2, 1 by 3, 1 by 4. You can have a cubic relation. So if A is say 2, 3 and 4, B will be 2 cube, 3 cube, 4 cube. Any relation, any rule to bind two sets. So A and B are now linked. A and B are now connected through this rule 2x. Right? Now, I will add one more element in B. One more element in B. I am adding number 10. Okay, I have kept a space here deliberately. I will add number 10 and keep it under circle. I have a reason for that. You'll see. Till now, we had A was 2, 3 and 4 and B was 4, 6 and 8. And we have seen and I have discussed that 2 is linked with 4, 3 is linked with 6 and 4 is linked with 8. 4 is the image of 2, 6 is the image of 3 and 8 is the image of 4 and this 2 is the pre-image of 4, 3 is the pre-image of 6 and this 4 is the pre-image of 8 and we have shown it here. Correct? Interesting? Chapter is interesting. Very new concepts, but I hope apart from, as I said, objective is to have complete mastery over the subject so that you do really well in the exam. Also, to get interest in mathematics so that it will help you in the remaining part of your CA. Okay. So now you see, we have seen the image and the pre-image column. We have connected A and B, but I have added one more element, 10, which is there in set B. Let's see what is the purpose. Now, we now understand two new concepts. See, you know the concept of dependent variable and independent variable. I think so. You know. Here, the moment I give you 2, you automatically, immediately calculate and you can tell me that, sir, the first element in set B will be 4. How you can do it? 2 into 2. If I tell you that one element in A is going to be 10, if I ask you that if I give you an element 10, what will be the image of that 10 in B? You will immediately tell me 20. If I tell you that, well, I have an element 15, 1, 5 in A, what will be the image of 15? You will tell me 30 immediately. 15 into 2 is 30. So image, pre-image, and this shows that the elements which are there in A is called the independent variable, whereas those in B are the dependent variable. These numbers which you see here, 2, 3 and 4, these numbers are also known as, these 2, 3 and 4 are also known as the domain of the function. Domain. Domain means the possible value which x can take. Okay? Domain. Please note, domain. Domain means the possible range of values which x can take. In this example, 3 values, 2, 3 and 4. Fine. And if I ask you, for the values 2, 3 and 4, what are the corresponding values in B? Okay, once again, for the values 2, 3 and 4, so if I give you the domain 2, 3 and 4, and if I ask you that what will be the corresponding values in B, oh, immediately will tell me, oh sir, the relation is 2x, so for 2 it will be 4, for 3 it will be 6, for 4 it will be 8. So the values in B, that is 4, 6 and 8, these values are called the range. What is my range? Okay? The range of vision, the range of numbers. So, domain is 2, 3 and 4. but the result 4, 6 and 8, this is called the range, R-A-N-G-E. This is called the range. So I can say that the domain is 2, 3 and 4 and the range is 4, 6 and 8. Okay, so domain and range I think you have understood. But I have included another element here, 10. 10 has no use because 10 does not have any pre-image. If I had given 5, then 10 would have made sense. Because you know 5 into 2 is 10. But I don't have 5 here. I only have 10 here. Fine. Domain. If I ask you, you will tell me, sir, domain I know. 2, 3 and 4. Very good. If I ask you, sir, range, you will tell me, sir, I know, yeah, 4, 6 and 8. But there is one more concept and that is called co-domain. Co-domain. Right? Co-domain. So if I ask you, domain is 2, 3 and 4, what is the co-domain? Co-domain will be 4, 6, 8 and 10. 4, 6, 8 and 10. So the co-domain will be 4, 6, 8 and 10. Okay? That means co-domain will be, first of all, this is the input. Okay? 2, 3 and 4 are the inputs. 4, 6 and 8 are the outputs. 2, 3 and 4 are known as the pre-image. 4, 6 and 10, 4, 6 and 8 are known as the image. 2, 3 and 4 are known as the domain. The output, 4, 6 and 8 is known as the range of the function. 2, 3 and 4 is the domain. 4, 6, 8 and 10 is known as the co-domain. So number of new concepts. I will take one more example because now we will get into some serious stuff. Okay? Right. I'll take one more example. So I rub this. I hope you have understood basic concept of what is domain, what is range, what is image, what is pre-image. Okay, now let us take one more example. Right. Let us take two sets A. 1, 2, 3, 4. 1, 2, 3, 4. We have B and we are having 1, 4, 9, 16, 25. If you see the relation A and B, A to B, the relation is x square. Because 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16. But I have 25. We will see why I have kept 25. So 1, 2, 3, 4. And here we have 1, 4, 9, 16 and 25. Okay. That means I can say, if I ask you that what is the function y is equal to x square. For every value, if x equal to 1, you have 1. If x equal to 2, you have 4. If x equal to 3, you have got 9. If x equal to 4, you have got 16. So 1 is linked with this one, 2 is linked with 4, 3 is linked with 9, 4 is linked with 16. So I can say, dear students, that 1, 2, 3 and 4 are the inputs. 1, 4, 9 and 16. 1, 4, 9 and 16 are the outputs. Okay? I can also say in the language of mathematics that x equal to 1, 2, 3, 4. 1, 2, 3, 4 is the domain. 1, 4, 9, 6 and 25. 1, 4, 9, 16 and 25 is called the codomain. So 1, 4, 9, 16, 25 are the are the potential output. But the real output, please see the difference. Potential output and real output. I have the numbers 1, 2, 3, 4. I have added 25. 25 is only a potential output. But the real output is 1 and 1, 2 and 4, 3, 9, 4, 16. So the real output is 1, 4, 9 and 16, and this is called range. Please note it down. Okay. So this is what is inputs, what is output, relation between two functions a and b. The relation is through x square. Last one we took was 2x, this time we take x square. Okay, we have seen domain, we have seen codomain, we have seen range. Right? So I hope you can see that the two sets, it's a case of mapping. This one is mapped to this one. 2 goes and gets mapped in 4. 3's mapping or 3's image is 9. 4's image is 16. But we don't have a pre-image of 25. Because we don't have, if we had got 5 here, then you could say 5 and 25 are linked. But since 5 is not there, the conclusion is that 25 does not have a pre-image in A. 25 belongs to set B, but it does not have a pre-image in set A. I hope it's clear. Once again, have a look at it. No problem. Inputs are 1, 2, 3 and 4. X has the value 1, 2, 3 and 4. Output is 1, 4, 9 and 16. Of course, plus 25 also because it's a potential output. 1, 2, 3, 4 is called the domain of the function, and 1, 4, 9, 16, 15, everything put together is the codomain, and actual output is 1, 4, 9, 16. 1, 4, 9, 16 is called the range. Okay? Okay. I hope this is clear. So we have talked about Venn diagrams, image and pre-image, domain, range, and also codomain. Big list. It's already 25, almost 25 new terms and new concepts. Quite a big list. This chapter is not so easy. It's quite complicated in the sense that so many terms, so many confusing concepts. So you have to be really careful in studying this chapter, and this chapter is the foundation for calculus. I think the next session possibly is on calculus, differential calculus and integral calculus. So this is the foundation to move into calculus. Okay, so this is what we call image, pre-image, domain, range. Now we look at, I'll just rub this part and we keep this example live in front of us and we move into 7.6. So now we move into 7.6 and we look at different types of function. Okay. So if you have two sets, now I'll be drawing like Venn diagrams, two sets. Okay. So you have two sets A and B. Okay. So I have 1, 2, 3, 4. I will write here 1, 2, 3, 4. 1, 2, 3, 4. I have the points here 1, 4, 9 and 16. Okay. So set A and B and the relation between them is x squared. Fine. Now please note, dear friends, that these 1, 2, 3, 4, please note that they have different elements in A are having different images in set B. So A is connected only with 1, 2 is connected only with 4, 3 is connected only with 9 and 4 is connected only with 16. This is mapping and the direction is this, of course. Right. This is called 1-1 function. That means one-to-one mapping. 1-1 function. Okay? So, one image. Different elements in A are having different images in B. So, it is a one-to-one, one-on-one. 1-1 function. Okay? Now, if it is such that, say, I have 1, 4, 9, 16 and I have another number that is also 16. I can always have two 16s. No problem. I will write one more 16 here. Okay. Okay. First let me take this one. I'll take one more 4 here. So now I have 1, 2, 3, 4 and 4. 4 comes twice. Okay? So there are 5. Now there are 5 elements. 5 elements in set A. 1, 2, 3, 4 and 4. 4 is coming 2 times. 1, 2, 3, 4 and 4. 5 elements. Now if you see the mapping, what do we get? 1 against 1, 2 against 4, 3 against 9, 4 against 16, but now one more 4 has come, so one more line I will draw and connect it with this 16. Please see. So now, this type of function, we call it onto function, onto. 1 and 1 function you have understood. Now this is called onto function, onto, also called surjective. Surjective function. Please don't confuse it with subjective. It is not subjective, but surjective. S-U-R-J-E-C-T-I-V-E. Surjective function. This is called one-to-one. Already we have done. Now this is surjective function, which means that every element here in Y is having at least one element in X, which is the image, pre-image. So every element in Y is having at least one image, which is called the pre-image. Of course, 16 has two images, pre-images. 16 has two pre-images, 4 and 4. So this is an example of onto function, or also called surjective function. So another example of onto function. So I'll just wrap this part and I'll show you one more example of onto function, or I think I can draw it here also. I'll just draw it here. So this relation you already seen. One more onto function. Okay. This is an important area of the chapter. So surjection, that is onto function, onto. This is here, I am coming onto, over, onto function. Surjection. So one more surjection. X, Y, Z and W, this is set A. The domain, pre-image. I draw the image now. 1, 2 and 3. X directly leads to 1. That means the image of X is 1. Image of Y is also 1. Image of Z is 2 and image of W is 3. Please see, X and Y both have the common image 1. Z has an image 2 and W has an image 3. Okay? X is 1, Y is 1, Z is 2, W is 3. This is called surjection. Very similar to what I did here. This is a surjection. Onto function. It is an onto function. Onto function. But I draw one more. Let's drop this part. I draw one more and let us see whether that is also a surjective function. This and this, A and B. I have X, Y, Z and W, and here I have 1, 2, 3 and 4. Please see carefully. X and Y are both linked with 1. Z is linked with 2 and W is linked with 3. Please see this once again. In this image which you see, X, Y, Z and W. This is set A. 1, 2, 3, 4 is set B. X, Y, Z and W. X and Y both have their image 1. Z has its image 2. And W has its image 3. So 4 which you see here, 4 is left alone. 4 has no companion. Everybody has a companion. Oh my God, 4 has no companion, alone. That means 4 has no pre-image in set A. So this case is not a surjection. It is not a surjective function because every element of B is not having a pre-image in A. At least one pre-image. For example, 4 has no pre-image in A. So this is not a surjective function. It is not an onto function. Okay? So we have learned, after codomain, we have learned onto function, one function. Onto function is also called surjective function. Okay? Now we see what is bijection function. Bijection. Bijection function is simple. I will just rub this part. The original picture which we had, the relation between A and B is x squared. So 1 has its image 1, 2 has its image 4, 3 has its image 9, and 4 has its image 16. Okay? Done? See if it is clear. 1 has its image 1, 2 has its image 4, 3 has its image 9, 4 has its image 16. So this is a one-on-one, one-to-one correspondence plus it is an onto function. Why? Because every element of B, set B, every element of set B has at least one pre-image in set A. So this is called, I will write this is a one-to-one plus it is an onto function. Both the characteristics. This type of function is called bijective function. So this image which you see is called bijective function. Okay? I hope you understand. See the diagram once again. You know 1, 2, 3, 4 is the pre-image. 1, 4, 9, 16 is the image. You know 1, 2, 3, 4 is called the domain. 1, 4, 9, 16 is called the range. Now you see 1 is linked. Companion. 1 is the image. 2's companion is 4. 3's companion is 9. 4's companion is 16. So it is a 1, 1 as well as onto because every person in B has at least one companion in A. Okay? So this is an example of bijective function. So we have done onto function, surjective function, and we have also done bijective function. So please remember bijective function means one function plus onto function. Both together gives you bijective function. Now, if you have something called onto, then you will have something inside. This is over, on. This is in, within. So we have something called into function also. Let's see that, into function. Okay, I'll rub this part. We'll understand what is into function. This is once again, dear friends, the toughest part of this chapter. and that's why already I think 2 hours is over, right? 4 o'clock, it's already past 4, and we have quite some things left today. A lot of things are still left and we'll complete. So it seems that 2 hours is not probably enough to cover such a huge area. Okay, so let's go into function now. Into function. Into function. I'll take some examples. A. You have an A. Set A. 2, 3, 5, 7. I'll take it 2, 3, 5, 7. You have set B. 0, 1, 3, 5, 7. 0, 1, 3, 5 and 7. Please see carefully. A is 2, 3, 5, 7. B is 0, 1, 3, 5, 7. And the relation between A to B is, the relation is fx is equal to x minus 2. So you have the values of x here, and B is the function of x where it is x minus 2. So when x is 2, so I will write a table here. Let us draw a matrix, a table, and see what will be the value of A and what will be the corresponding value of B, like we did for inequalities x and y. Right? When x is 0, what happens? When y is 0, what happens? Like that. So when x is 2, so when x equal to 2, x minus 2 becomes 0. 2 minus 2 is 0. Fine. When x is equal to 3, 3 minus 2 is 1. When x is equal to 5, 5 minus 2 is 3. When x is equal to 7, 7 minus 2 is 5. Okay? So, what type of situation do we have now? Well, 2 is linked with 0 because when x is 2, b is 0. When x is 3, b is 1. So when x assumes the value 3, it is 1. So 3 is linked with 1. When we have 5, it is 3. So 5 is linked with 3. And when you have 7, right? When you have 7, when x is 7, 7 minus 2 is 5. So 7 is linked with 5. But my dear students, please see that in B, in set B, we have one more 7, which is not having any pre-image in A. There is no one in A. There is no number in A which is linked with this 7. So, you have a number in set B which has no pre-image in set A. No pre-image. In case of onto function, I told you that in a situation where every element of set B, if it has at least one pre-image in set A, it's an onto function. Also called surjective function. Surjective. And this is an into function. Why into function? Because there is a number 7 in set B which has no pre-image. Absolutely no pre-image in set A. So this is an example of into function. Into function. Right? So I have discussed about onto function, one-one function, bijective function, surjective function, and now we have into function. Okay. Now we have one more, the last one, maybe the last one, let's see, I don't know. We have constant function, constant, okay, constant function. Now what is constant function? Okay, so into function is this, I'll just rub this part. Constant function. Now I have a relation between A and B. By the way, please refer, constant function is page number 7.11. Okay, I'm constantly referring to the study material. 7.11, constant function. Now constant function, let's see the concept of constant function. Okay, so let A have the values of x, and let me assume that the values are, say, I'll take any number, 1, 2, 3, 4. Chalo, 1, 2, 3 and 4. Any number. But the relation of B, of course, we will find out. What is the value of B? We will find out. I will just keep some space here to write about B. Okay, B I have kept some space, but I must define the relation between A and B. So the relation of A to B is what to write? X to the power 0. So I write y equal to x to the power 0. Be very careful and watch this. We are trying to understand what is constant function. So now, y is equal to x to the power 0. So I will again vacate these two columns and try to see what is the value of A and B for different values of x. Okay, so when A is 1, the function is 1 to the power 0. So when A is 1, B will have what value? 1 to the power 0 is how much? 1. Okay, I think anything to the power 0 is 1. So I will write 1. When x is 2, the next function is 2. 2 to the power 0. 2 to the power 0. That is also 1. When x is 3. 3 to the power 0. That is also 1. 4. When 4 to the power 0. That's also 1. 1. So now if you draw this, what will you get? If I draw this, what will you get? You will get something like this. So you have the values 1, 2, 3, 4. Okay. And this is the B. This is A and this is B. X is having the values 1, 2, 3 and 4. But whatever be the values of X, in B, there is only 1. Only 1. Because 1 to the power 0 is 1, 2 to the power 0 is 1, 3 to the power 0 is 1, so only 1. So we have only one image, that is 1. So this one is connected with this one, 2 is connected with this one, 3 is connected with this one, 4 is connected with this one, all are arrows. So can I say, dear students, that in this example A and B, right, I hope you can see clearly in this example. So I can say that this one which you see here is the image. It's the image of one, the same image 1 in set B. Same image. Same means constant. So this function is called constant function. It's on to what is constant function. So I keep on writing the areas we have covered, constant function. Now we shall move on to page 7.12 and see equal functions. Equal functions. 7.12. Page 7.12, please. And you will see what is equal functions. Now, two functions, if you have two functions fx and the other is gx, fx and gx. So this is a function, this is another function. These functions are said to be equal. So they will have an equal sign provided they have the same domain. If they have the same domain, now you know what is the domain. Like in this case A and B, 2, 3, 5, 7 is the domain, 0, 1, 3, 5 is the range. Okay. So if these two functions have the same domain, right, then they will be equal functions. Okay. Now 7.13, critical point, inverse function. This is fine, easy. Same domain and identical characteristics, equal function. Now we go to inverse function. Page 7.13, inverse function. Now friends, inverse function is also called anti-function. So this is inverse also called anti-function. Now you have these, you know, logarithms, anti-log. Okay, so we always use the word anti means opposite, right? So you are having a function and its inverse, the opposite. So it's a reverse function. Now, inverse function, so if it is say for example fx, the function is fx, the inverse is shown as f inverse x, f to the power minus 1, it's like that, inverse, opposite. Okay, here the cap is at the top, I tumble it down, so the cap is at the bottom, inverse. Okay, so this is called inverse function, but please remember that inverse function is only possible, relation is only possible when we have two conditions. It has to be a bijective function. So it will satisfy 1-1 relation plus on-to relation. When both are satisfied, only in that case we shall have inverse function. Let us see what is an example of inverse function. Opposite. I will take a simple example first. Okay, I'll just rub this part and discuss about the inverse function here. So we have already entered into the last part of our discussion, and that is relations to functions. Right. Let me take inverse function. A simple example. Say you have fx is equal to, say, 3x plus 2. What is the inverse function? So what we'll do is, let this is equal to y. So here you see, I am expressing y in terms of x. I am expressing y in terms of x. So I am saying y is equal to how much? 3x plus 2. Inverse function means I have to express x in terms of y. Okay, so what we do here, if y is equal to 3x plus 2, then I can say that 3x is equal to y minus 2, and therefore x is equal to y minus 2 by 3. Okay, so what I do is, to show the inverse function, instead of y, I will write x. Okay, this is the inverse function, I will write x. So I will say f inverse x is equal to x minus 2 by 3. This is how we write the inverse function. 3x plus 2's inverse is x minus 2 by 3. So here x is multiplied by 3. Please see, 3x plus 2 means what? X is multiplied by 3. Here I have divided it by 3. Inverse. Here 2 is added. Here I have deducted 2. Inverse means opposite. So I have found out the opposite from all angles. I'll take one more example. I'll take it here. This is, I think you have understood and you have noted it. So, you see, this is the last part of mathematics, and you know that after this we have calculus. We have the differential calculus and integral calculus. These three chapters are identically the toughest in mathematics. So, it's kept at the end. And if you look at our schedule given by BOS, these are at the end. So, you can understand, you have to study a little bit more. I hope you are following. I am breaking down each and every topic into as easy language as possible, assuming that most of you do not have a maths background, and these are tough concepts to understand. Even for people with maths background, even they will find it challenging. It is not a cakewalk, it is not a joke. So we are going as details as possible and giving as much of illustrations as possible. But please note, these three chapters are really serious affair, and a lot of concept is included. We have formula as well as concept. Okay, initial parts, okay, set builder, till I think union intersection, it is easy comparatively. But once you enter into these domain, range, image, pre-image, onto function, into function, bijection, surjection, constant function, matter becomes difficult. So first part, sets is comparatively easy, but as you move into relations and functions, it becomes serious. So I request you to also study and be positive, and slowly you will be able to understand. But for calculus, right, whenever you have the session, whoever takes the session, make sure that you follow each and every principle and practice along with the session, because these are the toughest part of this entire syllabus. That's of mathematics. Okay, I'll take one more example. Fx equal to 5x plus 3. I'll take fx equal to 5x plus 3. Now, so what I'll do is, shortcut method is, okay, I'll just write y equal to 5x plus 3. So I will find out, so 5x is equal to y minus 3. So x is equal to y minus 3 by 5. Now I will just replace y with x. So the inverse is x minus 3 by 5. So you can see what I have done. Here it was multiplication, here I have divided, here 3 was added, here 3 is subtracted. So f inverse x is x minus 3 by 5. That is how we solve inverse functions. Okay. So inverse functions, I will take, let's take one more example. The more we do, the more we clear our concepts. Okay. I'll take one more. Fx is equal to x minus 5 by 2. X minus 5 by 2. So just apply thinking. Here 2 is divided, x minus 5 is divided by 2. So what to do? We have to multiply with 2. So inverse function, f inverse x will be something like this, 2 into x, and 5 is deducted from here, so we will add 5. So it becomes 2x plus 5. As simple as that. Okay, so this is how we reverse. We reverse and find out the opposite relation or the inverse relation. Fine. But always remember that it has to be bijective. As I said, it has to be one-to-one and onto function if you want to find out the inverse relation. Fine. Now we come to the last part, that is reflexive, symmetry and transitive relations. And then we will go into the applications of mathematics using Venn diagrams, which is the last part. I guess it will take another 20 minutes at least to complete, right? And it's a heavy chapter, and as we move along, you can see so many new concepts. So constant function we have seen equal functions also, right? And we have now done the last part, let me write it, that is inverse function. Inverse function we have done. And now we move on to reflexive, symmetry and transitive. So reflexive, heavy words, really heavy words. Let's see if we can make head or tail out of it. Reflexive. Then we have symmetry. Okay, symmetry means symmetrical. Reflexive is reflection. Symmetry is like a butterfly, symmetry. Okay, butterfly. Transitive. Symmetry, T for. Reflexive means you see your reflection. Okay? You see your reflection in a mirror. Still water, you stand, you see your reflection. Okay? So reflection means related to itself. Okay? So related to itself. That means 1, 1, 2 to 2. This is a reflexive. Symmetric means related to another element. Symmetry. Like a butterfly, see. Okay? Butterfly. Symmetric. Any letter, say you take the letter E. Symmetric. You just break from in between. O. It is symmetric. D. It is symmetric. You cut across. Okay? So you get symmetry. Therefore, symmetry means related to any other element. So, related to any other element. That means if I write 1, 2 and then 2, 1. 1, 2, 2, 1. Symmetric. Okay? Now let us see what is transitive. Transitive means, I will use the word, you see, transition. Transition means what? you are transitioning from a student slowly to a professional. Transition is moving, transition. Okay? A child transitions into an adult. Transition is to move on. So transitive means that if 1, 1 and 1, 2, then 2, 3, then 1 also equal to 3. If a relation is there, 1, 1, between each other, between reflexive, okay, then you have 1, 2, 2, 1, symmetry. 2 to 3, then automatically 1 to 3 also will be there. And 1 to 3 means 1, 2, 3. Not 1, 2, 3, but 1 from 1 to 3. 1 to 3. So the relation 1 to 3 will be transitive. Transitive. Now I'll take an example. Okay, illustration. This is definitely a challenging part to understand. Please support and put in your best efforts. So I'll take a simple set A. I'll take 1, 2, 3. Now if I write a set R1 which is related to A, and if I write, please be careful, look at these relations. If I write 1, 1, then I write 2, 2, then I write 3, 3, and then I write 1, 3. This is case number 1. I am writing case number 1. Set R1, original set is 1, 2, 3. Original set is 1, 2, 3. The first set R1 is 1, 1, 2, 2, 3, 3, 1, 3. 1, 1, 2, 2, 3, 3, and 1, 3. So this is an example of what? Now is it reflexive? Reflexive means 1, 1, 2, 2. Okay, 1, 1, 2, 2, 3, 3. Yes, it is reflexive. R. Yes. Is it transitive? 1, 1, 2, 2, 3, 3. We have 1, 3. Yeah, it is transitive. But is it symmetric? Symmetric means 1, 2, 2, 1. But here we have 1, 1, 2, 2, 3, 3, 1, 3. We don't have, if it is symmetric, it will have 1, 2, 2, 1 also. But we don't have symmetry. So symmetric not. So it is reflexive, it is transitive, but not symmetric. Second case, I write R2. R2 I will write like this, 1, 1, 2, 2, 1, 2, and 2, 1. 1, 1, 2, 2, 1, 2, and 2, 1. What type is this? What type of function? 1, 1, 2, 2 means it is reflexive. 1, 1, 2, 2. 1, 2, and 2, 1 means it is symmetric. 1, 2, 2, 1. But we don't have the relation of 1 and 3. So the second case, if you see, we are having 1, 1, 2, 2. Okay? But do we have, this is 1, 1, 2, 2, 1, 2. 1, 1 we are having, 2, 2 we are having, 1, 2 we are having, 2, 1. So is it symmetric? Yes, it is symmetric because we have 1, 2 and 2, 1. Okay? Is it transitive? Let's check. It is transitive, 1, 2, 2, 1 is there. But is it completely reflexive? Because you need to have, if you want to have reflexive, you need to have 1, 1, 2, 2 as well as 3, 3. Here we have 1, 1, 2, 2, but we don't have 3, 3. So it is symmetric and transitive but not reflexive. And the final case, I will take here R3, and R3 I will write 1, 1, 2, 2, 3, 3, 2, 2, 3, 3. So 3 and 3, and then it will be 1, 2, 2, 1. 1, 2, 2, 1. 2, 3 and 3, 2. A long one. So the R3 set is 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 2, 3, 3, 2. So first of all, please note 1, 1, 2, 2, 3, 3. So 1, 1, 2, 2, 3, 3. It is reflexive because reflexive means 1, 1, 2, 2. It is reflexive between each other. So it is reflexive R. 1, 2, 2, 1, 2, 3, 3, 2. So it is symmetric also. It is symmetric because symmetric means 1, 2, 2, 1. But question is it transitive? Because in case of transition, you also need to have 1, 3. 1, 3 is not there because transitive means to move. So 1, 2, 2, 3 automatically means 1, 2, 3. 1 will go from, so I said 1, 2, 3. If I write 1, 2, 2, 3, it means 1 is linked with 2, 2 is linked with 3. So 1 is also linked with 3. Okay? That is called transitive. Move, transition, moving. Right? So this is an area, in this third case, you can see it is reflexive. It is also symmetric but not transitive. Not transitive. So this is the toughest part. And now we have FOG and GOF. Now we go to the composite function. Okay, so I will write here, we have completed RST as well, reflexive, symmetric and transitive functions. Now we will go to complex or composite functions. I think this is the last part and then we have the applications, numericals and applications. Let me go to the composite function. So now you have basic understanding and working knowledge of what is functions. Functions can be of different types. I can write functions as fx, it can be x square, right? Function fx means you can write y equal to x square. It can be 1 by x, it can be log x, it can be x to the power 0, anything, right? It can be root over x, x plus 3 for example. So any function. Now the question is, what happens if I write, it comes in the exam. What happens if I write, two functions are there, gx and fx. We are now dealing with composite function. What I wrote just now is functions. But now we are dealing with composite functions. Composite. C-O-M-P-O-S-I-T-E. Composite functions. In short, we call it FOG and GOF. FOG and GOF, FOG and GOF. What is FOG and GOF? Let's see. Okay, so say I write fx, function of x, a particular function of x equal to 3x minus 2. Okay? Another function of x. So it's like x has two friends, fx and gx. You can always have two friends. You are studying two subjects. Mathematics accounts. So fx is 3x minus 2 and we have gx equal to x square. Two different functions. Please write. Now we will find out what is FOGX, F-O-G-X. F-O-G-X. Right? We will find out. F-O-G-X. FOGX, FOGX means, what is FOG? F of G, the function of Gx. Okay? So like you say in Facebook, you have friend. You have friend's friend also. That friend may not be connected to you. Social media. Friend of friend. Similarly here it's function of function. Okay? Function of function. Function of Gx. Now it means f of g, FOG means actually f of gx. F of gx. That means you put gx value into fx. You just take gx, put it into fx. Pick up gx, put it into fx. Pick up gx, put it here. Pick up and put it. So, the main function is 3x minus 2. So if I take gx equal to x square, I will put x square in place of x. I take gx, throw it into fx. Pick up gx, throw into fx. That is fog x. So if I substitute x with x square, then I will get the answer fogx is 3x square minus 2. I am taking another example. So I hope this is understandable. I hope you are following it. Sure. F of gx. Function of gx. Function of x means what? If you give a value of x, you will get function of x. So here f of gx. So gx you put into fx. fx is 3x minus 2. Put x square in place of x. You get 3x square minus 2. Okay. Now we have another one. I'll take fx is equal to, just write it here. Fx is equal to 2x plus 3. Okay. Fx. Now I'll just draw a line here. So fx is equal to 2x plus 3. And gx is equal to 3x plus 2. Fx is equal to 2x plus 3 and gx is equal to 3x plus 2. So we have to find out, this was fogx, now we will do gof, fog opposite, gof, gof. So gofx. It was function of gx, it is now f of gx, this is now g of fx. That means I will put fx, here I was putting gx into fx. Here now I will take gx. Gx is ultimate. It is actually g of fx means g of fx. So I will take fx and put it into gx. Now actual gx is what? Gx is 3x plus 2. This 3x plus 2. So instead of x here, I will take 2x plus 3 and put it here. So it will become 3 into 2x plus 3 plus 2. That gives me 3 2s are 6x plus 9 plus 2. That is, it gives me 6x plus 11. This is what is called GOF and FOG. Function of GX and G of fx. Okay, two function. It is called composite function because we are trying to find out the composite function. Okay. Yeah, now it is the last, finally 7.17, page 7.17. Right? So G of f and f of g I will write here. So GOF and FOG. So dear students, we come now to the last part, and this is the problems and solution using Venn diagram. Please move to page 7.17 of your study material. Page 7.17 of your study material. Okay, now we go into applications. And we will try to use Venn diagram and simple logic to crack some of these questions. Some of them are tricky questions. Let's see. Okay. I think the first one, example 1, which you see on page 7.17 of your study material, 7.17 of your study material, page 7.17, example is 1. Okay. So the question is, out of a group of 20 teachers in a school, 10 are teaching mathematics. Fine. So you have 20 teachers, 10 are teaching mathematics, 9 are teaching physics, and 7 are teaching chemistry. 4 teachers are teaching mathematics and physics. Okay, so I'll just write mathematics and physics. So M intersection P, mathematics and physics, but nobody is teaching both mathematics and chemistry. So mathematics and chemistry, 0, no one. So they are asking, the question is, how many teach only physics? So only physics is how much? and how many teach chemistry and physics? So P intersection C is what? So let's see the question once again. 20 teachers. So that gives you the size of the universal set, 20. Okay. Complete set is 20. 20 teachers are there. 10 of them are teaching only mathematics. Great. You have 9 teaching only, once again, 9 teach physics and 7 teach chemistry. Okay. 9 teach physics and 7 teach chemistry. Fine. 4 of them are teaching both mathematics and physics, but nobody is teaching mathematics and chemistry. We have to find out these two. How many teach only physics and how many are teaching both physics and chemistry? Okay. So, what to do? Now, if you draw a Venn diagram, let's try and draw a Venn diagram. Okay, so we have physics, chemistry and math. So I draw one circle, another circle, and then we have another circle. So physics P, chemistry is C, and mathematics is M, right? So you have physics, chemistry and mathematics, 3 subjects, 3 circles. We are drawing a Venn diagram. Now let us see, the question is, we are assuming we have to find out P intersection C. How many teachers are teaching both physics and chemistry? So let it be X. Okay, so P intersection C is assumed to be X. P intersection C, this and this is assumed to be X. Now the question is, 10 are teaching mathematics, 9 teach physics and 7 teach chemistry. Now mathematics and chemistry nobody is teaching. So mathematics and chemistry nobody is teaching. Okay, fine. So nothing to write here. Question is, 7 teach chemistry. 7 teach chemistry. Out of them X is the common part. So this remaining part is 7 minus X. If you leave aside the common part, 7 minus X. 9 are teaching physics. Okay, 9 are teaching physics. And we have 4 teaching mathematics and physics. Physics and mathematics, it is 4. Okay, so this part is 6 and this part is X and this part is 4. Right? So physics and mathematics 4. And we know that chemistry and mathematics, there is no one. None teach chemistry and mathematics. So this is no one. So, please see once again. We are having, that means this remaining part, the people who are teaching only physics will be, the question says that 9 teach physics. But 9 teach physics means this full circle is 9. It includes X and this 4 also. So, people who are teaching only physics, their number is 9 minus X minus 4. Now the question is, 10 teach mathematics. Mathematics we know 10 people are teaching. So this full is 10 and this part is 4. So the remaining part is 10 minus 4, that is 6. So we have got these figures. We have physics, chemistry and mathematics. The common area, physics and chemistry. Physics and chemistry assumed to be X. So this part is X. Mathematics and physics, we have 4 who are common. Chemistry and mathematics, nobody is common. There are no teachers who are teaching both of them. Now we have total mathematics teacher is given 10. 4 of them are common. So teachers who are teaching only mathematics is 6. Similarly, teachers who are teaching only physics is 9 minus X minus 4. Because 9 teachers are there who are teaching physics. 9 minus X minus 4. And we have 7 minus X who are teaching only chemistry. So, if altogether we have 20 teachers The equation is now like this. 9 minus x minus 4 plus, you have 6 here, so the 6 plus you have 7 minus x here, 7 minus x, plus this common part which is 4, plus this x. So plus 4 plus x, this becomes 20. So I am taking this part, 9 minus x minus 4, I am taking this full x, I am taking this part which is 4, nobody is in this part, okay, it is given. We are having 7 minus x is this part, I have taken 7 minus x, and 6 is this part. So I have taken 6 also, and now let us solve for x. If you solve it, let's see what we get. 9 minus x minus 4. So it gives you 5 minus x plus 6 plus 7 minus x plus 4 plus x equal to 20. So you have 5 plus 6 plus 7. That is 13 and 5, 18. 18 and 4 is 22. Minus x minus 2x plus x. So 22 minus x is equal to 20. So we get x is equal to 2. So x is coming to 2. X is 2, which means there are 2 teachers who are teaching both physics and chemistry. So 2 teachers, x is 2. And we have to find out how many teachers are teaching only physics. So only physics is 9 minus x minus 4. That means now it is 9 minus 2 minus 4. That is 3. So we have 3 teachers who are teaching only physics and 2 teachers who are teaching both physics as well as chemistry. So this is, you can see it becomes easy once you apply the Venn diagram. Right. Now let us move to the last, almost the last example for today. We'll take 2 more, winding up at 5. Okay, and let's take number 2. This question says, a survey shows that 74% of the population, they like grapes. They eat grapes. Okay. 68% like bananas. 68% of the population like or eat bananas. What percentage of Indians like both grapes and bananas? So grapes, we can call it a set of G, and this bananas, we can give it a name B. So we have to find out N, G plus B. Okay. Now we know that 74% like grapes and 68% like bananas. Now N, G plus B is basically equal to 74% plus 68% minus those people who like grapes and bananas. Okay. So the total amount is 100, we know 100 population. So this will be 74 plus 68 minus 100%. So that is 74 and 68 is, you have 2, 142. So 142 minus 100. So you have 42% who are liking both grapes and bananas. What's percentage of the Indian? So this is basically G intersection B. They like both grapes and bananas. Now the total we know is 100. Okay. And we know the formula Mg union B is equal to Mg plus Mb minus Mg intersection B. This is the formula we have done. A union B, G union B equal to G plus B minus G intersection B. That means G intersection B, which we have to find out. Now G union B is 100. We know G is, only G is 74 and only B is 68. So you can easily find out what is the amount of G intersection B. 74 plus 68 minus 100. Okay. Right. We take few questions from the exercises. Okay, we're devoting around 10 minutes for that. Right. So we have come to the end of the chapter, and great congratulations to all of you that you are there with me and helped in completing this chapter. So GOF, FOG we have done, and at the end we did the Venn diagram analysis, so applications, apps. We have done the apps as well. Okay. So anything which is left out, let me see quickly. Reflexive is done completely. Reflexive, symmetry, transitive is done. Composite function is done. Fog and GOF is done. And we have done the applications as well. Okay. So we take the questions from the exercises. First one, let me take is exercise 7A, number 1, page 7.6. So now it's time for some exercise. So it is 7A, and it is number 1. Okay, number 1. Number of subsets. Please open 7A, number 1. Number of subsets of the set 2, 3, 5. So the set is given 2, 3 and 5. So number of subset is what? Options are 3, 8, 6, none of these. We know that the formula is 2 to the power n. Number of subset is 2 to the power n, and number of proper subset will be 2 to the power n minus 1. So here the question is subset. 2 to the power n is 3. So 2 to the power 3, that is 8. So answer is 8. Number 1 is done. Number 19. N into n plus 1 by 2, and n is a positive integer. Is it a finite set? Is it an infinite set? Is it an empty set? None of these. Now, if n is a positive integer and the set is the set of n into n plus 1 by 2, means you know it is the sum of the numbers, right? We know that the sum of the even number is n into n plus 1. The sum of the odd numbers is n squared, right? And we also know that 1 plus 2 plus 3, if you go on, odd and even, you are getting n into n plus 1 by 2. So it is a positive integer. And for square, you know n into n plus 1, 2n plus 1 by 6. Fine. So this is the sum of the positive integer. It becomes a series. The question is n, we don't know, it will go on. So n is a positive integer. Definitely is not an empty set. Now it can be finite as well as infinite. Question is, given the question, n is a positive integer, then it can take any value. So ideally it will be infinite set, because n can take any value and n can tend to infinity. But if you talk about finite, means which is countable, which has a limit. Infinite is which has no limit. Now, if it is a positive integer, very difficult to say. But only thing is, it can be, depends on the intention of the question setter, you know. Because the language is such that it can have two types of answers. It all depends on what the question setter wanted to ask from me. Now, n is a positive integer. Positive integer can take any values, it can tend towards infinity. Strictly speaking, if you can limit n, then it becomes a finite set. But if you cannot limit n, and if n tends to infinity, then of course it becomes infinite. Okay. Let's take number 21 now. A union A is what? A union A is what? A union A is nothing but A itself. Okay. I take number 22 now. A intersection A is what? A intersection A. So if you find out the common parts of A and itself, so A intersection A is A again. Right. Now we are taking example 7A, number 31. Okay. Set is given 1, 2, 3, 4. So the set is given, E is given 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. The set is given. And there is a subset of E which satisfies the equation 5x plus 10 is greater than 5 plus x 5 plus x is greater than 10, what will be the subset? Set is given 1, 2, 3, 4, 5, 6, 7, 8, 9. And the equation is given 5 plus x is greater than 10. 5 plus x is greater than 10. What will be the subset? So the subset will be, subset SS is equal to 5 plus x should be greater than 10. So if you take 5, it will be 10. So if you take 4, it will be less than 10. So if you take 6, it will be 11. 5 plus 6 is 11. That is more than 11. So 6, 7, 8, 9. This will be the subset. 6, 7, 8, 9. So that you can satisfy this given condition. Okay. Now we are taking exercise 7b. Okay. We move to 7b. Yes. Yeah. Just completing in 2-3 minutes. 2-3 minutes. Okay. So we'll have to stop here. I'll just take 2 questions from exercise 7b and complete. Okay. Exercise 7b, the last 2 for the day. I'll take number 6 first, and the domain is given, a function is given 1, 7 and 2, 6. Okay, so what will be the 1, 7, 2, 6? So what will be the domain? 1, 7 and 2, 6. Okay, 1, 7 and 2, 6. So in this case, what is the domain of this function? So the domain will be 1 and 2 and the range will be 7 and 6. Because here you can make out that 1 and 7 are related, 2 and 6 are related. So 1 and 2 will be the domain and 7 and 6 will be the range. And the last one we will take is example 7b number 10. Example 7b number 10. Example 7b number 10. The question is fx. Fx is equal to 1 by 1 minus x. 1 by 1 minus x. Then f minus 1 equal to what? Fx is equal to 1 by 1 minus x. So f minus 1. So when fx is this, if you put x equal to minus 1, if you put x equal to minus 1 in this expression, you will get f minus 1. So let us do this. You will get 1 by 1 minus 1. Instead of x, we will put minus 1. So this gives you 1 divided by 1 minus minus 1, that is 1 plus 1, that is half. Okay. So our team will have to close now because our team has some other assignments back to back. So I'll just quickly refresh yourself. We started with set, discussed about well-defined set, elements. We went into roster form, set builder method of forming sets. We went into subset, superset concept, discussed about it. Then we proceeded to discuss in detail about proper subset, equal set, equivalent set. Thereafter we moved into complementary set, P dash. Then we had concept of universal set, which I discussed. Then I took the example of null set and the number of subset, which I did here, 2 cubed equal to 8. Thereafter we moved into the cardinal number of the set and we discussed about power set. Then we moved on to the set notations, union, intersection, null set, and of course we talked about the theorems 1 and 2, that is N, A union B, and then we proceeded to talk about product set, Venn diagrams, image and pre-image, domain, range and codomain, and then we moved on to the functions where I discussed about 1-1 functions, onto functions or surjective functions and into functions. Then I discussed about bijective function, moved on to constant function, equal function, inverse function, and then we discussed one of the most challenging parts, that is reflexive, symmetric and transitive. Reflexive is reflection, symmetry is this, and transitive is to move. So we discussed about it, and then we talked about composite function, and we ended with the applications where I took 2 cases. One with the grapes and the bananas example, the other with the professors of physics, mathematics and chemistry, and we did examples 7a and 7b. So with this, dear friends, we come to the end of today's session. Hope to see you soon. And till that time, go through the chapter. Once again, read through, practice the problems, and take care. See you. Bye.